Hi, good day everyone. So let's continue our discussion on the first law of thermodynamics. So now let's discuss four kinds of thermodynamic processes. So there are four specific kinds of thermodynamic processes that occur often in practical situations. So we have this adiabatic process, isochoric process, isobaric process, and isothermal process. So, unsay kalayan sa upat. So, for adiabatic process, we have to take note that sa adiabatic, Q or heat must be equal to 0. So, there is no heat transferred into or out of the system. So, kung may kong adiabatic gani, automatic your Q is equal to 0. Okay? So Q is equal to 0. So using first law of thermodynamics, when Q is equal to 0, then it means that the change of internal energy must be equal to the negative work done. Okay? So that's adiabatic process. For isochoric process, the volume must be constant. So when the volume is constant, work done is equal to 0. So for isochoric process, uh, when the volume remains constant, and it implies that the work done is equal to 0. Since Newton's work is related to the change in volume, we have pressure times dV. Okay, pressure times dV. So when there is no change in volume, then work is equal to 0, and that is isochoric process. For isobaric, pressure now is constant. So when pressure is constant, it implies that work can be reduced into this form. Work is equal to constant pressure P times the change in volume. We have V2, the final volume minus initial volume. That since your pressure is constant, then you can actually integrate the dV, and the integration of this dV results to this V2 minus V1. So ito isobaric means pressure is constant, and for isothermal, we know this one. Isothermal, it means that your temperature is constant. So again, there are four kinds of thermodynamic processes. Adiabatic, it is when heat is 0. Isochoric, it is when volume is constant. Isobaric, it is when pressure is constant. And isothermal, it is when temperature is constant. So for example of adiabatic process, so we have this, when the cork is popped on a bottle of champagne, the pressurized gases inside the bottle expand rapidly and do positive work on the outside air. There is little time for the gas to exchange heat. So it means na your heat is approximately equal to 0. Kaya wala na kay oras, wala na kay time since sudden kayo ang process, wala na kay time for the gas to exchange heat with their surroundings. So the expansion is nearly, take note, nearly adiabatic. It is when Q is equal to 0. There is no exchange of heat. Hence, the internal energy of the expanding gas decreases. So when heat is equal to 0, then the delta U is equal to negative work and the temperature drops. This makes water vapor condense and form a miniature cloud katong pagkuhan mo sa core. So muna ang nahitabo, and the process is adiabatic. For isobaric, most cooking involves isobaric process. That's because the air pressure above a sauce pan or frying pan or inside a microwave oven remains essentially constant when the food is being heated. So isobaric means pressure is constant. So ang iyang application is kaning nasa cooking tuan. So the four processes on a PV diagram, so makita nimo ang upat ka graph dari makita nimo tanan process in this PV diagram. For constant pressure, it means isobaric ang imong process. So this one is isobaric process because your pressure is constant. So when you move from state A to state number 3, that is isobaric because your pressure is constant. And for this one, this curve here, okay, from state A to state 2, this process is an isochoric process because your volume is constant. Okay, at least from state A to state 2, it is an isochoric process. Adiabatic, if we have this A from A to state 1, at this curve, your heat here is equal to 0. In isothermal, we have the state A from state A to state number 4. It is when your temperature is constant, meaning the temperature at point A must be equal to the temperature at point number 4. Okay, point number 4. So we have 4 adiabatic, isobaric, isochoric, and isothermal. Now let's talk about internal energy of an ideal gas. We have to take note that one of the special properties of an ideal gas is that its internal energy depends only on temperature, not on its pressure and volume. So we will use this one later. Kaning statement that the internal energy U does depend on only on its temperature, not on pressure and not on its volume. That is for an ideal gas. Okay, so magamit natin siya later. Solving for heat capacities at constant pressure. So we have to take note that internal energy depends only on temperature. Okay. Okay, so let's now have these heat capacities of an ideal gas. We recall that for CV means molar capacity at constant volume. We derive this one. Sa ito ang last na discussion, na-derive na ito sa CV for monatomic gas is equal to 3 halves. It is constant. It is equal to 3 halves R. And for diatomic gas, CV is equal to 5 halves R. Okay, so na-derive na ito siya last na ito na discussion. Now, we will talk about CP. CP means molar heat capacity at constant pressure. So what will be the value of the CP, the molar heat capacity at constant pressure? No? For monatomic gas, this is equal to 5 halves R, and for diatomic gas, CP is equal to 7 halves R. Why? Notice, si CP for monatomic gas is mas dako siya compare sa CV for monatomic gas. How to derive? Yun sinip pag-derive nganong for monatomic gas nganong 5 halves R ang imong CP, 7 halves R ang imong diatomic gas. So basically, we will relate now the CP and the CV. So relate na to unsay relationship aning CV and CP. So how to derive these two? Now, if we recall, we have this heat in terms of CV. We know this one, dQ is equal to mc delta T, or you can write this in terms of CV as mCV dt. For constant volume, dQ is equal to mCV dt. Now, using first law, if we use first law of thermodynamics, okay, ito itong first law is we have this, du is equal to dQ, the internal energy is equal to the heat minus the work, okay? And at constant volume, we have to take note, at constant volume, what will happen to work? Work is equal to 0 because this W is equal to 0 because there is no change in volume. since your work can be written as PdV, and since there is no change in volume, then this will be equal to 0. So what will happen to the first law? The first law now becomes this: du is equal to dq, which is equal to ncv dt. So therefore, du, the change of internal energy, can be written as ncv dt. Okay, so later we will use this one at constant pressure. Take note, we have to take note that the internal energy is equal to ncv dt. And one property of an ideal gas is that the change of internal energy thus depends only on its temperature. Now, for Cp, we have this. Cp, itong Cp, this is the molar heat capacity at constant pressure. We can write dq as mc delta T, or in terms of Cp, you can write this as ncp dt. We know how to derive this one. Okay? Nag-derive na ito sa last na ito ng mga discussion. So dq is equal to ncp dt. At constant pressure, we can write dq as ncp dt. Gapon. At constant volume, you can also write dq as ncv dt. Okay? At constant pressure, the work now is not equal to 0. So the dw is not equal to 0, but it is equal to P times dv, because pressure lang man ang constant, dili constant ay mga volume. So dili mag-0 ang ako ang work. And we have to take note also that for ideal gas, kung kadumdum mo, ideal gas, we have this ideal gas equation, PV is equal to nRT. And at constant pressure, P is constant, meaning only is your volume will change. If your volume will change, your temperature will also change. So we have this. You can write this as PdV, nag-change yung volume. This is equal to nR, only the temperature will change, not the pressure, because pressure is constant. So therefore, you can write for the ideal gas equation as this: PdV is equal to nRdT. And what is PdV? PdV is just the change of work. So therefore, the work now can be written in terms of temperature, take note, can be written as nR dt. So we know dW, we also know dQ. We also know dQ. dQ is equal to ncp dt. Ang kulang na lang is ang du. What is du? du, sa itong gingon ako ngayon, ang isa sa properties ay mo ang change of internal energy of an ideal gas is that du depends only on temperature. Okay? Thus, the change in internal energy during any process, take note, any process, must be determined only by temperature change. So therefore, sa untang process, at constant pressure mo siya, at constant volume mo siya, and so on, du must be the same, and it is only dependent on its temperature. So therefore, pwede na ako masulag si du as equal to ncv dt. Muna ito na-derive sa atong last nga slide. Isa kung sa nga process, balag dili pa constant, balag constant pa yung volume or what, si change of internal energy is dependent lang siya sa imong temperature. Okay? So therefore, you can write du as equal to ncv dt. So nana ko du, nana ko dq, and nana ko dw. Now the first law becomes this. So the first law becomes, so ito, du is equal to dq minus dw. du is equal to ncv dt. dq is equal to ncp dt. And my work is equal to nR dt. And from this, Notice murag makancel imong n and dt, right? Na common term. Na ako'y n rin, ako'y dt, n dt, n dt. So ang mabili na lang is we have this. The relationship between Cp and Cv is equal to this. Cv is equal to Cp minus R. Transpose the R, we have Cp is equal to Cv plus R. So this is now the relationship between Cp and Cv. So mo ni karon na for monatomic gas, kung kabantay mo monatomic gas, Cv is equal to 3 halves R. So therefore Cp is equal to 3 halves R plus R, which is equal to 5 halves R. So this is for monatomic. For diatomic, na ako'y Cv is equal to 5 halves R. Plasan lang ni mo R, makuha ni mo si Cp equal to 7 halves R. So that is why ako'y makuha nga Cp 5 halves R for monatomic, 7 halves R for diatomic. Okay? So gingana na pag-derive ang Cp for monatomic and diatomic. So we have to take note the relationship between Cp and Cv. This is Cp is equal to Cv plus R. Now we have this ratio of heat capacities. It is denoted by gamma. So gamma is just equal to Cp over Cv. For monatomic ideal gas, the gamma here is equal to 1.67 since gamma is equal to Cp over Cv. Cp for monatomic gas is 5 halves R, while Cv is 3 halves R. So this is equal to 5 over 3, which is equal to 1.67. For diatomic, na ako'y Cp nga 7 halves R divided by Cv nga 5 halves R. This is equal to 7 over 5, which is equal to 1.40. Notice, kabantay taan ni sa last na ito nga subject, gamma is equal to 1.4. Nagamit natin ni siya sa katong speed of sound. If you recall, the speed of sound is equal to square root of gamma RT over M. And we used gamma as 1.4 because ang air is i-consider nato siya nga diatomic gas, diatomic ideal gas. That is why ang atong gigamit sa unang value for gamma is 1.40 in order to solve for the speed of sound. Okay, so nagyapoy rason nganong 1.4 ang atong gamit ato. So nay rason nganong 1.4. It's because air is considered as diatomic ideal gas. Okay. So these are the molar heat capacities at low pressure na sa corresponding ratio of molar heat capacities. So for diatomic, for monatomic, and for polyatomic. Okay, for example, so we have a typical dorm room or bedroom contains about 2,500 moles of air. So this is my M, 2,500 moles. Find the change in internal energy of this much air when it is cooled from 35, take note, 35 to 26 degrees Celsius at constant pressure of 1 atm. Treat the air as an ideal gas, diatomic ideal gas, where we can use gamma as 1.400. Okay, so ang gipangita, solution. So ang gipangita ani is ang change of internal energy. And it is equal to NCV dt, right? That the change of internal energy is equal to NCV dt. We know N is 2,500 moles, and the dt is the difference of temperature from 35, initial na 35 and final na 26 degrees Celsius. But we don't know CV, o patakabalo sa CV. Pero, masolve na ko sa CV using this. Solving for CV, solve for CV, take note that the ratio gamma is equal to Cp over Cv, okay? And Cp can be written as Cp plus R, Cv plus R over Cv. So you can write this as 1 plus R over Cv, right? Okay, so gamma is equal to 1 plus R over Cv. Transpose na ko ni dito, na ko this becomes gamma minus 1 is equal to R over Cv. Okay, and then Cv over R, yan Cv over R is just equal to 1 over gamma minus 1. Sakto? So therefore, Cv is equal to R over gamma minus 1. And we know R is 8.314 joule per mole Kelvin. And the gamma here is 1.4 minus 1. So Cv is equal to 20.79. 20.79 joule per mole Kelvin. So once makuha na ko si Cv, makuha na ko si du now, the change in internal energy is equal to N, which is equal to 25 mole, okay, times the Cv na 20.79 joule per mole Kelvin times the change in temperature nga 26 minus 35 degrees Celsius. So therefore, the change of internal energy is around negative 4.68 times 10 to the 5 joules. So this is now the change. In order to change its temperature from 35 to 26, meaning pabugnawon nimo imong bedroom, kinahanglan ka mo remove energy nga around 4.68 times 10 to the 5 joules. So that is the change in internal energy. Okay. So last we have this adiabatic process for an ideal gas. We have to take note that for an adiabatic process, Q is equal to 0. As shown in this PV diagram, we have this adiabatic expansion from point A to point B. For an ideal gas, an adiabatic curve at any point is always steeper than the isotherm passing through the same point. As the gas expands, it does positive work on its environment, so its internal energy decreases and its temperature will drop. Note that an adiabatic curve at any point is always steeper than an isotherm at that point. So one example of adiabatic process is we have this exhaling adiabatically. We have this. Put your hand a few centimeters in front of your mouth and open your mouth wide and exhale. Your breath will feel warm on your hand because the exhaled gases emerge at roughly the temperature of your body's interior. So kung munganga ka, exhale ka, dakoy mo ang baba, feel mo is init ang ang gibuga sa imong baba. Now purse your lips as though you were going to whistle. So kanino, gamay kayo ang opening. And again, blow on your hand. The exhaled gases will feel much cooler. Mas bugnaw siya kung maghuyok pa gani. Sapa. Why? Because ang process nga nana is adiabatic. In this case, the gases undergo a rapid, essentially adiabatic expansion as they emerge from between your lips. So the temperature of the exhaled gas decreases. So that is why mas bugnaw siya, no? Mas bugnaw siya kung ang imuhang paghuyop isingani. Kung paghuyop man, no? That's why mohuyop ka kay bugnaw ang temperature sa gas nga gigawa sa imong lawas. Compare sa kaningan. And the process nga nadira is adiabatic process. And that ends our discussion on first law of thermodynamics. Thank you and God bless.